Hello. This will be a demonstration of proposition 1017 of Euclid's Elements, which says, first of all, that if to the greater of two unequal straight lines, a rectangle equal to the fourth of the square on the less be applied, deficient by a square figure, and if such application, if this cut the greater straight line into parts which are commensurable with one another, then the square on the greater straight line will be greater than the square on the lesser straight line by the square on a straight line commensurable with the greater straight line. Got a long enunciation. There's a lot of moving parts going around here. There's some talk of application and deficiency, which we haven't seen since book 6. So let's draw it out. We're going to have two unequal straight lines, BC and A, of which BC will be the greater. So let's put A will just be floating up here. And next, we're going to apply a rectangle equal to a fourth of the square on A and deficient by a square figure. What that's going to look like is we're going to cut BC, say at D, such that the rectangle contained by BD and DC, were we to complete it, would be equal to a fourth of A squared and would fall short of covering the whole line BC by a square figure which may be imagined as such, right? We got a right angle here. So we have greater straight line BC, lesser straight line A. We're going to apply this rectangle contained by BD and DC. It'll cut BC into those two parts, BD and DC, such that BD times DC, the rectangle contained by BD and DC, is equal to a fourth of A squared, and it will not cover the whole straight line BC, but rather will fall short by the defect of DC squared, which I've drawn as a dotted square instead of a full square. Furthermore, let it be the case that BD and DC, the parts into which this rectangular application has cut BC, let these two straight lines BD and DC be commensurable with each other, from which we will prove that BC squared is greater than A squared by the square on a straight line commensurable with BC. First, we're going to bisect BC at E, like so. BE will be equal to EC. Furthermore, we will cut off the straight line EF equal to DE. So, like such that EF is equal to DC. Okay? Now, since BE is equal to EC, BE is equal to EC, and EF is equal to ED, from our construction in our first step, we can say by common notion 3 that the remainder BF is equal to the remainder DC. BF minus EF has to be equal to EC minus ED by common notion 3, and that produces the straight lines BF and DC, which have been found equal to each other. Furthermore, because these straight lines are equal to each other, the sum of BF and CD will be twice CD, and therefore will have to CD the ratio which a number has to a number, because it'll be a ratio of 2 to 1. It'll be a double ratio. Therefore, we'll be able to say that CD is commensurable with CD plus BF by proposition 10(6). Now, because BC has been cut into equal parts at E, right, BE is equal to EC, and we're assuming the more likely case that BD is unequal, it is not equal to DC, we could imagine a special case in which they were equal, in which this proposition would be shorter, but it hardly is worth a mention. So let's say that BE is equal to EC by virtue of step 1, and that BD is not equal to DC. Then the straight line BC, it's been cut into equal parts at E and unequal parts at D, which means we can say, according to proposition 10.5 of Euclid, that the rectangle contained by the unequal parts, BD and DC, plus the square on the segment between the points of section, which here is ED squared, will be equal to the square on the half, here EC squared. In total, BD times DC, the rectangle contained by BD and DC, plus ED squared is equal to EC squared. Now, if we multiply this whole equation by 4, nothing will change. It's a property of magnitudes that we can do that. Quadruples of equals are also equal to each other. So that we can say that 4 times the rectangle contained by BD and DC plus 4 times the square on ED will be equal to 4 times the square on EC. Now, 4 times the rectangle BD times DC is equal to the whole A squared, because we know that the rectangle from our given, the rectangle BD times DC, was given as equal to a fourth of A squared. So 4 times such a rectangle will be equal to the whole A squared. Furthermore, because DF is double the length of ED by virtue of how we made EF in our first step, we know that 4 times the square on the half ED will be equal to the whole of the square, or the square on the whole DF. So that 4 times ED squared is equal to DF squared. And similarly, because BE is equal to EC, so that BC is double EC, 4 times EC squared is equal to BC squared. So by common notion 1, we can substitute these into our equation and say that A squared, which is equal to 4 times the rectangle BD times DC, plus DF squared, which is equal to 4 times the square on ED, is equal to BC squared, which is 4 times the square on EC. AC squared plus DF squared is equal to BC squared. Now, all that remains for us to show in the first part of this proposition is that BC is commensurable with DF. Now, because BD was given as commensurable with CD, we know from proposition 10.15 that if 2 magnitudes be commensurable, then their sum is commensurable with each of them. So that because BD is commensurable with CD, the whole BC is commensurable with CD. Now, because CD was shown to be commensurable with CD plus BF in our second step, we know from proposition 10.12 magnitudes commensurable with the same magnitude are commensurable with one another. We can also say that BC is commensurable with CD plus BF, which then also means by 10.15, remember it's one of those propositions that includes its own converse, because BC is because BC is commensurable with CD plus BF, it must also be commensurable with the remainder of BC minus CD minus BF. BC is commensurable with BC minus CD minus BF. If we look at the straight line BC minus CD minus BF is just the straight line FD. So that BC is commensurable with FD. So that BC squared, which remember is equal to A squared plus DF squared. It is therefore greater than A squared by DF squared. BC squared is greater than A squared by the square on a straight line commensurable with BC, namely FD, which is what we wanted to prove. So we're done with the first part of this proposition. You might have noticed I've been referring to this as the first part of the proposition because, much like 10.15, which was earlier mentioned, this proposition includes its own converse. We've shown that our enunciation up here is true, and the second part of this video will be to show that, that the converse of this enunciation is also true, or the partial converse of this enunciation is true. So having shown that the first part of this proposition is true, I will therefore cut the video here and move on to the second part of proposition 10.17. Now, on the other hand, conversely, if the square on the greater straight line is greater than the square on the lesser straight line, by the square on a straight line commensurable with the greater straight line, and if there be applied to the greater straight line a rectangle equal to the fourth part of the square on the less and deficient by a square, then the greater straight line will be cut into parts commensurable with one another. Just as last time, we'll set out two unequal straight lines, BC and A, of which BC shall be the greater. And again, just as last time, we will apply the rectangle BD times DC to BC, such that it is both equal to a fourth of A squared, and such that it is deficient. It does not cover the whole of the straight line BC. It is deficient by CD squared. Furthermore, let it be that BC squared is greater than A squared by the square on a straight line commensurable with BC. From this, we will show that the parts into which BC has been cut, namely BD and DC, we will show that BD is commensurable with DC. Now, just as last time, we will accomplish a similar construction bisecting BC at E and making EF equal to ED, from which we will show in the same manner as the first four steps of this proposition that A squared plus DF squared is equal to BC squared, from which we can conclude, because BC squared is greater than A squared by the square on a straight line commensurable with BC, that BC must be commensurable with FD. Now, since BC is commensurable with FD, by proposition 1015, it must be commensurable with BC minus FD. BC is commensurable with BC minus FD, but BC minus FD is the sum of the straight lines BF and DC, so that BC is commensurable with BF plus DC. And it was shown in the second step of this proposition that BF plus DC is commensurable with DC, so that BC is also commensurable with CD according to proposition 1012. Now, since BC is commensurable with CD, BD must be commensurable with DC. This is what proposition 1015 tells us. Because BC is commensurable with CD, then the parts of BC, namely BD and DC, must be commensurable with each other, so that because BC is commensurable with CD, BD is commensurable with DC. This is what we wanted to show, so we're done with the second part of the proposition. And this being the final part of the proposition, we're therefore done with the whole proposition, therefore, etc., QED. There only remains one last thing to be shown about this proposition, namely that when we apply this rectangle to BC equal to fourth of A squared, that part doesn't actually matter. If we apply this rectangle to BC such that it is deficient by a square figure, it does remain to be shown that the area of this rectangle that we've applied is equal to the rectangle contained by the parts into which the straight line to which we've applied it are equal. Fortunately, Euclid does supply us a short lemma, about 10 lines, proving exactly that. So, having finished the second part of this proposition, I will now demonstrate that lemma. Now let us demonstrate that lemma, which says that if to a straight line there be applied a rectangle deficient by a square, the applied rectangle is equal to the rectangle contained by the parts of the straight line to which it is applied. Well, the straight line AB, to which we will apply the rectangle AD deficient by the square DB, something like so. See, we've applied this rectangle AD, we've put it on top of the straight line AB, but it's deficient by a square DB, and this will cut the straight line AB at C. And we will want to show that the rectangle AD is equal to the rectangle contained by AC and CB. Euclid says that this is at once manifest. For because DB is a square, by virtue of our given, DC is equal to CB. Now the rectangle AD, we know it has to be a rectangle because the angle DCB is a right angle, and the sum of the angles ACD, DCB have to be two right angles. If one of them is a right angle, the other one has to be a right angle, therefore AD is a rectangle. Because the rectangle AD is contained by AC and CD, and we've just shown that CD is equal to CB, It is therefore the case that the rectangle AD is equal to the rectangle contained by AC and CB, simply exchanging that containing side CD for CB, to which it is equal. So again, that the rectangle AD is equal to the rectangle contained by AC and CB, which is what we desire to show. So we're therefore done with the lemma, therefore, etc., QED. And having demonstrated this lemma, I've demonstrated the whole of proposition 1017. So I'm going to end the video here and move on to proposition 1018.